This aerial view shows a common profile for modern LNG carriers: long, flat deck covers that hide the cargo containment systems below. Holding thousands of tons of liquid at minus 162 degrees Celsius inside a moving hull requires managing a specific structural risk. Standard ship steel exposed to those temperatures undergoes sudden brittle fracture and can fail under normal operating loads. To manage this, naval architects utilize two opposite structural philosophies, both positioned beneath the main deck. First, the membrane system. Its 1.2 millimeter tank walls force the ship's hull to carry the cargo structural load. Second, the independent system. This self-supporting structure stands on its own cradles, physically separated from the hull walls by an air gap. Both architectures are approved under the IGC Code and are common across the global fleet. The core distinction between every gas carrier comes down to where the load terminates. Does the tank support itself or pass load to the hull? A membrane sheet typically measures between 0.5 and 1.2 millimeters in thickness. At this dimension, the sheet cannot bear the structural weight of the cargo. Instead, the membrane functions as a liquid-tight, flexible liner. The load path is direct. Static cargo pressure pushes against the membrane, passes through the load-bearing insulation blocks, and terminates at the ship's rigid hull steel. This design must account for thermal contraction. Steel cooled to minus 162 degrees shrinks, causing massive stress if rigidly fixed. The gas transport system uses INVAR, a near-zero expansion nickel-steel alloy. Other designs use corrugated stainless steel, flattening like an accordion to absorb physical changes. The Technigas Mark III system is the most prominent example of this corrugated stainless steel approach. The insulation layer behind the metal must perform two tasks. It must block heat transfer to the cargo while remaining rigid enough to transmit millions of tons of pressure into the hull. Builders typically use perlite-filled plywood boxes or reinforced polyurethane foam to meet these load-bearing requirements. Because the ship's hull provides the strength, membrane vessels do not require heavy internal bulkheads for support, which increases the available cargo volume. A membrane system effectively turns the ship's structure into the containment vessel itself. Independent containment systems operate on a different set of physics. These tanks are self-supporting. They sit inside the hold space, separated by a clear air gap. Cargo pressure is contained entirely by the tank's walls. Weight transfers vertically into base support cradles, ensuring no lateral pressure reaches the ship's sides. To handle thermal contraction, these tanks actually move. As steel shrinks during cooldown, the tank slides on keyways integrated into its supports. This mechanical isolation requires specific trade-offs. You are building a second steel structure inside the ship. This increases the vessel's light ship weight and reduces the internal volume available for cargo. The benefit is structural decoupling. If a stress fracture develops in the tank, those forces are not transferred directly into the hull. Independent tanks sacrifice internal volume to keep the physics of the cargo separate from the integrity of the ship. If the primary tank ever leaks, the ship must be protected from the cryogenic liquid. The IGC code requires a secondary barrier to contain leaks. The design is determined by cargo temperature, with a threshold at minus 55 degrees Celsius. For cargoes like LPG, which boil warmer than minus 55 degrees, the requirements are different. On these vessels, the ship's inner hull itself is legally allowed to act as the secondary barrier catching a leak. However, the inner hull must be built with low-temperature steel specifically rated for that exposure. Standard steel becomes brittle at these temperatures. The code ensures the hull can maintain its ductility even if a leak occurs. For cargoes colder than minus 55 degrees, such as LNG at minus 162, the hull can no longer serve this function. At these extremes, a separate secondary barrier must be built into the insulation system to ensure the ship's steel is never exposed to the liquid. Structural redundancy is dictated by the absolute temperature of the cargo and the threshold for cryogenic embrittlement. There is also a hybrid third option, the semi-membrane tank. In a semi-membrane tank, the flat sections rely on the hull for support like a membrane, while the curved corners were thick enough to be self-supporting. To verify the mechanics, in a membrane design, which structure bears the cargo's structural load? The hull. The membrane is only a barrier for the liquid. This creates the containment matrix used today. Membrane tanks are hull-supported, independent tanks are self-supported, and semi-membrane tanks are a hybrid. This structural split is the primary distinction between the gas carriers in operation today. However, independent is a broad category. Under the IGC Code, it is divided into 3 distinct subtypes. Types A, B, and C each utilize different engineering standards for structural analysis and pressure ratings. In the next episode, we will look inside these 3 designs to see how fracture mechanics and pressure thresholds change the rules of shipbuilding.